after the explicit method, we're going to see here the fully implicit method to solve the Black-Scholes equation. So this is the Black-Scholes equation, and the fully implicit method is going to be basically the same as the explicit method, but the only difference is that the finite difference representation that we are going to find for both the second order partial derivative of b with respect to s and the first order partial derivative of b with respect to s are going to be evaluated at time j plus 1, while in the explicit method it was evaluated at time j. That's the only difference, because otherwise the finite difference representation that we are going to take for all the partial derivatives arising in the Black-Scholes equations are going to be the same. And besides that, here everything here on the right is going to be evaluated at time j plus 1. So everything here that A, B, C are going to be evaluated at time j plus 1. That's the only difference. So considering that, I'm plugging in this equation that final difference representations we do have for these partial derivatives. The results that we do have for the final difference representations basically this is the one. Okay, as you can see here, the A, B, and C are evaluated at the time principal at time j plus 1. So in this case, it's true that as the simplest case where the volatility or the interest rate and independent of time, that we see there is no difference in these coefficients, at least with respect to the explicit method, so that this an evaluated at time j plus 1 is going to be 1/2 sigma squared times s squared, and s squared is n squared times delta s squared. On the other hand, this bn evaluated at time j plus 1 is going to be r times s, so times n delta s. On the other hand, the c, which is going to be cn at j plus 1, is going to be minus r. So these are the ones that we need to plug here in order to have the definite expression. So from here, as you can see, everything here in all the expression we do have here, everything depends on j plus 1, but this one. So what we can have is just clear from this expression, this v evaluated at n and j, and this we can bring to the other side, and the result we have of this v evaluated at n j as a function of different values of the options evaluated at time j plus 1 will be given here. It's interesting to see as well as it happens in the explicit method, the accuracy of this ordering this equation, for example, in order to have the value of the option at time n and j, even the square of delta t and delta t times the square of delta s. Besides that, we do have this new one and new2 arising here. New 1 is delta t over the square of delta s, and new 2 is delta t over delta s, in the same way that we defined for the explicit methods. So we have here, that's the final difference representation that we do have. It's interesting to have in mind that this equation here, all this equation here, holds for n index going from 1 to ns minus 1. So we cannot apply that for n equals 0 or n equal ns, because you can see here, applying that to n equals 0, we can have that from here, we'll have n minus 1, and applying that to n equal ns, here we'll have ns plus 1. So, and these two values, they are not defined, so that's why we cannot apply for these two indexes. So here we have like ns minus 1 equations, therefore, and the number of unknowns we have at any time is ns plus 1. So again, we have that these two equations, these two extra equations that we need, are coming from the boundary conditions as it happens with the explicit method. And as we already know, considering the experience we do have for the advection equation and the diffusion equation, there is a huge difference between explicit and implicit methods. One is because of the stability. It's highly improved when implicit methods are considered. And on the other hand, the solution procedure. In the case of the explicit method, it was much more straightforward. It's not the case of the implicit methods, because remember that here we have an expression for this v evaluated at j as a function of different values of the option evaluated at j plus 1. But actually what we do want is just the opposite, because we want to have the next time value of the value of the option at the next time step as a function of the value of the option of the previous time step. That's actually what we do want. But there's no way of getting an explicit solution of these equations, yes, of the v evaluated at j plus 1 as a function of some v's evaluated at j. So we need to apply here a different procedure in order to overcome that difficulty and apply that procedure, that method. And this one will be based on the matrix representation of this full implicit method that we'll see next.